quite as far as I'd like. I think I only gave you 16 problems on this. I'm going to ask for them by Thursday, and I can't move that deadline. So I'm not following the order in the book. It seems more logical to me, since we've already done power series. And for power series, the main tool that we needed was the ratio test, right? So since we already did that, we're going to stick with power series for a moment here and do part of this section. Because this section is about doing what we've been trying to get to the whole time, representing functions with series, right? That's kind of been one of our themes, how to represent functions with series. We're going to represent functions first with power series. That turns out to be a somewhat limited thing, so what we're going to do next is looking at representing functions with what are called Taylor-Maclaurin series, which is much more generalizable to pretty much anything. So then we'll go do all the Taylor-Maclaurin parts next. Okay? So that's the idea. So to open this up, I think that we can just think about a friendly series that we've seen in the past. What is that thing? That's a geometric series in the standard form, and I even have it's equal to its convergent value, if of course r is less than 1, right, the ratio. So there we go, that's a familiar piece of information. So I think we can use that in terms of power series to model functions, basically. Okay, and here's how we're going to do that. It involves lots of clever algebra. When we do Taylor-Maclaurin series, we're not going to have to be as clever. Actually, it'd be nicer, easier. But we got to be a little bit clever on this one. So I'm saying we can represent, we'll do 2 examples if we have time. So we can represent something like this, now using a power series. That's a function, right? What kind of function is that? Some kind of version of 1 over x, right?
Is that radical? What is that?
Rational, right? Fraction, rational function. So I think a lot of rational functions can be modeled this way. It's probably still not the best way to do things. Taylor-Maclaurin's really the way to go, but this is a good intro, okay? So why does that function, you see kind of, how it kind of matches? So I think this is kind of like a geometric power series. Yeah. In fact, it's equal to the power series, this one specifically. Which one specifically? Can you guys help me?
X to the n.
1 over x to the n?
1 over, oh, 1? 1 over, right? 1 times
1 over x to the n?
x to the n. Because remember, the way that geometric series worked, it converged to this value, and a was what? Sometimes it's called a sub 1 for the first term, and r is the ratio between terms in that series. So since this looks like the convergent value, I think you can say that this power series, as long as you make that its first term, right? If you plug in 0, our first term will be 1, and then this is like r. In fact, this looks like what if we start writing it out? Plug in 1 plus fen is 1 x plus fen is 2 x squared plus x to the third. And remember, the whole power that we want to keep in our mind, the reason you'd want to do this in the first place is if you go like maybe out to maybe even x to the 9th, cut it off right there, that's going to approximate this function, which is the beauty of this, why we're doing this, okay? The only thing that's a little bit sneaky on this is this thing, the ratio has to, we have this that we had to stick with, right? So what's that mean about this one? What's r in this one? X, so that says this only applies to what interval? That's the reason this isn't the best. This only applies to that, and maybe we'd have to check the edges or something. So this power series only approximates that function in a pretty limited area of the real number line, you know what I mean? As soon as we go outside, like to 2 or 3, it's not going to do a very good job anymore. So this is kind of limited the way we're starting out here. Okay, you've got to worry about your ratio, your interval of convergence, I should say. Okay, but you can fix that and make this same thing apply to other intervals. It's just kind of a pain, and this is the way we're going to start. So let's pick. Let me write it in a different color. So let's choose another interval. Let's say we don't really need the function to be, we don't really need its value over here. What if we need like in the neighborhood, let's pick a new interval. Pick the interval, how about like centered at, that one's centered where? 0. Let's pick centered at like -1. What if we need to be over in that area and use this function over there, okay? I think we can probably fix this thing up. We just got to use a little bit of clever algebra, maybe some clever ones and stuff, right? So we had this. You guys agree that this is the same? Yeah? If you go -1, 2 minus 1 is 1, minus x. It's the same, right? Why am I doing that?
So now it's
Because I shifted it.
Because now where's the new center? That's got a now center of -1. Does it fit the form for geometric convergence? Almost. What's the problem, Paul? In geometric convergence, this can be anything and this can be anything, but that has to be 1, so how can I fix that?
Pull it out of 1/2.
Go 1/2 just down here? You gotta make it legal, you guys know that, right? Clever one. So what does that come out to? 1/2, write it like that. That becomes 1. And we could even put this in our parentheses if we want, right? It's not squared or anything. Even if it was squared, we could still fix that, right? You could pass it in and make that a 4 if it was squared. That'd still be okay, so you could do those ones. You'll have a couple problems like that. Now it's in this form. So that's now equal to what? What series are we talking about there?
1/2.
1/2.
X plus 1 over 2 is it?
X plus 1 over 2 is the ratio to the nth power starting at 0. And if you're unsure, geometric series always start at 0 if you write them in the right form, but just think about this. If you plug in 0, do you get 1/2 as the first term? Yeah, we can start plugging stuff in, right? You plug 0 in, you get 1/2. If you plug 1 in, you get 1/2 times x plus 1 over 2. If you plug 2 in, you get 1/2 times x plus 1 over 2 squared, and then we'd have to start simplifying this to make it easier to see. Does that make sense? We good? But we know that this guy definitely converges to this value, which simplified becomes this function. So this is kind of like backwards intuition, isn't it? But it's still pretty neat stuff. So now this power series will approximate that function, but not in this neighborhood. In what neighborhood?
X plus 1 over 2 is less than
For x plus 1 over 2 is less than 1, so we could go that, right? So that says x plus 1. Oops. So x is less than 1 to -3. So that's kind of better for a couple reasons. It accomplishes what our original goal was, which was to evaluate the function in the neighborhood of -1, but it's also a little wider, isn't it? So this is just extensive algebraic cleverness. The nice thing about Taylor and Maclaurin series will be you don't need to be nearly so clever, but this is really neat to think about. So pretty good stuff nonetheless. Let's see if we can do maybe one more today. We good? So, love this stuff. So one more problem. So let's say we find a power series for a new function. Let's just say we have the traditional 1 over x function, which of course is going to look like that. It's a nice parent function, you guys know, right? Let's say, well, we know we can't do it everywhere a lot of the time, so we are going to pick our battles and say, well, we need to evaluate that function.
Centered at.
You can pretty much do this centered at anywhere. The problem with this technique over Maclaurin and Taylor series is you kind of got to do it every time over again, and that's not what your calculator does. Your calculator is way more efficient. It actually doesn't have very much memory. It couldn't handle this, but good to think about still. Okay. So So let's say we want to center it at 1. Any ideas? So let's just start out like last time. Start out with the function you want. And what's our main goal? To kind of make it look like...
You could put x minus 1 in there. Sort of.
So we want an x minus 1, so it's centered at 1, so good. We want an x minus 1, right? Because that'll make it centered at the right spot. Important, but how do we do that?
Adjust that, so add 1 again on the bottom.
So we should add 1 again, so it's legal. Oh, that's kind of like... Is that it?
Negative.
Is that the way it needs to be? What's geometric converge to? Remember, we're going for a over 1 minus r. Does that fit it yet? Pull out, what are you talking about, Brenna? Like this?
Make it -1.
So we want a negative right there, right?
Yeah.
We don't want to touch this. So maybe we could like turn this around. Go 1 minus x. Same thing algebraically, but now fits the form. Clever. Good. So now we just say, okay, as a series, we know that that is the convergent value of the series that is geometric with 1 as its first term and its ratio as 1 minus x, starting at 0 and going to infinity. Yeah? Oh man, I'm starting to get excited. I really like this stuff. I'm sorry if I'm too excited for you, if you can't handle it. We could start looking at a few of the terms if we're a little shaky. We should probably write out a few terms, right? So plug in 0, we get 1. Good. Plus plug in 1, we get 1 minus x, right? Plug in 2, you get 1 minus x squared, 1 minus x cubed, plus dot dot dot. And you can start using some new notation. You can, of course, like start running the ratio test on this, but I'm going to let you get away with shortcuts because you're just going to be saying, where was this centered again? Centered at 1. The notation you can use for centered at 1 is, you can just say, what did I say? I guess I didn't use it yet. So 1 minus x is less than 1. You could just go like that. If you want to solve this down, you can. So what would we say? 1 minus x. I guess it's good to solve it down too. Minus 1, that's 0. Minus 1, that's -2. So x divided by -1, what happens? Okay. So that says 0 to 2. It's centered at 1. Okay. So if we went outside of that window, we'd have to redo something to get it to converge to the right value again. Okay? So that's the idea. So we'll work on like another example like that tomorrow, but I think you're set to do most of the assignment.
So all these are going to deal with geometry?
Yeah, they're all going to be geometric pretty much. I think the first 4 problems, I will do number 3 with you guys tomorrow, but the first 4 problems say do it this way, okay? And then also confirm that you get this series by doing long division. So I'll show you how to do that tomorrow. So you can do it this way, and then also you could actually use long division in a strange way that you probably hadn't considered to get the same series. So I'll show you that. That's kind of like an alternative and pretty neat. That's what we'll do tomorrow. Okay? But you guys, so if you want to do like get started, as I would recommend, then just ignore the long division, leave some space on 1 through 4. Okay? You can do it the other way. Cool. So let's guys do Thursday.